Hello, good morning. Today, we're going to look at chapter number 15, which is direct current circuit. Under direct current circuit, we have altogether 6 subtopics. Okay, and number 1 is internal resistance, which exists in the battery, electric potential, Kirchhoff law, which is quite difficult in this topic, and then potential divider. We are going to understand what is the meaning of balance bridge and so on. And then we have wisdom bridge, and finally we have potential meter. Under the wisdom bridge and potentiometer, we're going to have their own applications. Okay, so we're going to start with number 1, internal resistance. Normally the symbol we use for internal resistance is small r. Okay, small r. Now, to understand internal resistance, the first thing that we need to look at is we try to understand the difference between ideal battery and the real battery. So meaning is, what is ideal battery or ideal cell? Okay, as we know, under in a battery, how it works is this: most of the battery that we have in the market are based on chemical reaction. Okay, so this chemical reaction will convert the chemical energy into electrical energy when the cell is put into use. So theoretically, ideal battery has efficiency of 100%. Okay, 100%. Okay, but in reality, this is not the case. Okay, because in reality, we are dealing with real cell or real battery. Okay, or real cell. So the difference between real cell and real battery and ideal battery is the efficiency will be always less than 100%. Okay, because of the transfer of charge through the chemical itself, the flow of ions and electrons is actually facing difficulty. So this difficulty is because of the what we call that, the collision between the chemical and the ions and also the electron. So that one is the one that causes the existence of internal resistance. All right. So now, real battery, as we know, is the actual battery that we use in the lab or in our daily life. Okay, but battery we have so many types. So first we look at type of battery. Okay, type of battery or cell. Okay, so there are first type actually discovered is actually the lead acid battery. Okay, lead acid battery, but of course this is another category because it is rechargeable. And then number 2 is the zinc carbon. Okay, the zinc carbon battery. Okay, so this zinc carbon battery is the most common battery before rechargeable cell is being marketed in the commercially. Okay, and then after that we have this type of battery. We call that one the nickel cadmium battery, and then followed by number 4 is the nickel metal hydride battery. Okay, and lastly it followed by the lithium battery. Okay, and of course under lithium battery we have so many type of technology. We have a lithium ion battery, we have lithium ion polymer battery. The purpose of all those advanced battery is actually to reduce the risk of fire, okay, or explosion, because lithium from the periodic table is actually a very what we call it, very active ingredient in the battery itself. So this type of battery is of course have a very high energy density, but the problem is it have to be used properly with a proper charger and so on, so that it don't catch fire and cause a lot of problem afterwards. Alright, so that one is a type of battery that we have. Some are rechargeable, some are not. For example, this one is rechargeable, this one is not, this one yes, yes, yes. So why rechargeable battery? Because rechargeable battery in long term is more cost effective and is more or less like environmental friendly compared to the other zinc carbon battery, which when the power is low, then we just discard them away and then in a rubbish bin, and then finally they end up in a dump site, and finally return to us in contamination. Alright, so that is a zinc carbon battery. And another type which I didn't mention here is the button cell. Button cell is the one we use in our watches and so on. They are very small, and that one, when they are first invented, they contain a little bit of mercury, but now we don't have it anymore. Okay, so the mercury is actually been banned from being mixed into the chemical of a battery itself. Okay, so those are also having non-rechargeable and rechargeable type. Alright, so that is the type of battery that we have. If you look at it carefully, all these are based on chemical reaction. Some chemical reaction go one direction. For example, zinc carbon in one direction, and then lead acid, nickel cadmium, nickel metal hydride, and lithium battery. This one can go two way. You use it, it's called discharge. When you need to put power in, it's called charging. So that charging and discharging have, of course, a certain limitation. You cannot just stay the charging forever. Alright, so it's a chemical cell anyhow. Alright, so now all of them having chemical inside. So all of them is actually resisting the flow of ions and also electron within the cell itself. And this phenomena is what we call the internal resistance. Okay. So now we're going to look at the internal resistance, the effect on the battery and also the external circuit. So the effect, of internal resistance in the cell. Okay, the effect of internal resistance in the cell. Alright, now since we know that internal resistance is actually a type of resistance, resistance means the ability of the material to resist the flow of charge. It's either the ions or inside the for the electron also. Now that resistance, we cannot eliminate them. There's no way in science that we have, and also in the technology that we know of, there's no way that we can actually get rid of internal resistance, but we can reduce them. Okay, so that's why different type of cell have their different value of internal resistance. Of course, the one that with the least internal resistance here, you'll be surprised, is the lead acid battery, which has a history of more than 100 years. So why lead acid battery compared to other cells have a very low internal resistance? Because the lead acid battery, the electrolyte used is in liquid form, which is the diluted sulfuric acid. But the rest doesn't mean that they have don't have liquid at all, but they are liquid absorbed in certain type of chemical. They are in a high moisture environment. So it's just like our toothpaste you use to brush your teeth. Now that is inside those other cell other than lead acid battery. Okay, so the cell, okay, that we're talking about here is the real cell or real battery, which has internal resistance R. Now you have to remember the concept that from the previous chapter, if we have current flowing through resistance, what happens is the current, okay, that flow through the resistance R, of course, part of the energy will actually be converted to heat. Okay, so that means heat will be generated when you have resistance in the circuit. Well, that's the job of the resistance anyway, is to produce heat. Okay, it's not something that is actually very beneficial for a circuit. So that's why in the design of circuit, we are trying to reduce the resistance as much as possible. But it's quite impossible to reduce them to zero. Okay, so this amount of heat is actually directly proportional to the current, okay, and also the time of the flow of the current. So the effect is, that means if this is inside the battery, okay, and let's say this is a battery, and the battery is connected to external circuit and current started to flow. When current is flowing, it also produce heat, and this heat is actually coming from the battery itself. So this is called internal heating, and the battery will warm up. When the battery warm up, that will actually cause other problem in the battery, like if the current is too big, then the heat produced will be too high, and finally maybe the chemical reaction will be ceased. That means it's not because temperature too high, the chemical reaction cannot occur, or maybe during that heat production, there's not fast enough for the heat to be dissipated to the environment, so the battery heat up to a condition that the liquid inside there or the moisture inside there started to vaporize, and it caused high pressure, and finally the battery exploded. That can actually cause something very dreadful to the battery, and if you are like nearby to that battery during the explosion, it might cause injury and maybe even death, right? So that is the effect of internal resistance to the cell. Normally it just simply warm up the cell or heat up the cell, but that is a type of wastage. Okay, it's a waste to have internal resistance. But what can we do? Chemical reaction all have internal resistance, so there's no way we can actually get rid of them, but we can reduce them by finding better alternative of all the chemical we use inside there. Okay, but of course hundreds of year technology that we have come to quite a high level of advancement in battery technology. Okay, for example, lithium ion, and maybe next time you're going to have another type which we call the graphene. Okay, graphene battery. So this is quite a new technology, graphene technology, but not many countries have that technology to deal with because it's quite a high-tech problem. Okay, so that is the effect of internal resistance for the cell. Alright, so the next thing is we're going to look at how are we going to like solve problem that involve internal resistance. In Form 4 and Form 5, you learn something about battery, but mostly ideal battery. So that's why you can use ordinary Ohm's law, V equal to IR, to solve the problem. But the problem now is the battery itself also have internal resistance. So theoretically, we have to take into consideration the internal resistance when we do calculation in the problem. Okay, so we start with this one, E, the formulation of R, internal resistance. Alright, so let's assume you have a battery, okay, and you have an internal resistance. So normally battery have something that we call the EMF, okay, and that is the symbol we use, and internal resistance is small r. And let's say we connect it to an external resistor, so we use a big capital letter R. Alright, now there are two things that we want to connect to the circuit. Number one is the ammeter, okay, ammeter to measure the current flow, and then another one is a voltmeter, okay, a voltmeter. So this voltmeter, which is connected to the P and the Q, is used to measure the voltage across the resistor R. Okay? So let's say we know the value of the EMF, okay, of the battery, and we can actually take the reading from the voltage from across the R. We assume that is V big R. Okay? And from experiment, it's very obvious that our VR is going to be less than our EMF of the cell. Okay, it doesn't make sense, you see, because when you connect directly to the cell, we don't see any resistance, okay, or resistor attached to the cell, because this thing is inside the battery. So sometimes we use a dotted line in the form of a box to represent that this internal resistance is within the battery itself, which there's no way to take it out. Doesn't mean that you operate the cell, you open up, there is a little small resistor. It's not like that, okay? So since we cannot take it out, so normally when we connect the external resistor to the cell, that is what we get. We assume that since this one also connected directly to the cell, so their value is supposed to be the same, but they are not. Okay, the reason is very simple. Internal resistance actually absorb part of the voltage. So to understand that, then we have to redraw the diagram by theoretically taking this one out. So now we have a new diagram for our battery. Emitter, this is our P, this is the big resistor, and this is our Q, and this is our internal resistance of the battery. Theoretically, now this battery become ideal because you already take out the internal resistance. Alright? So now imagine that we have two voltmeters. One is to measure the voltage across the external resistor, big R. Another one is to measure the voltage across the small r, which we assume we can take it out. Okay, so this is VR. Now you can see very clearly in the theory of circuits, we know that this is happening. Okay, because there's no more resistor attached to the battery, so we know that this 2 point here is actually directly connected to the battery. So that means the voltage across here plus this one must equal to the EMF. So it should be like this. VR plus V small r must equal to epsilon. Okay. So now VR is equal to epsilon minus V small r. But from Ohm's law we know that VR is equal to epsilon minus IR. Okay. This is I, this is R. So you can see that if you connect an equipment to a cell or battery which has internal resistance R, and if you operate the equipment at high current, this multiplied by the internal resistance of the battery, you're going to minus it from the EMF, and that means it causes more drop. The higher the current, the larger the drop in the voltage across your external device. So that's why we can never get the voltage reading to be exactly the same like the battery reading. Conclusion is you cannot actually use voltmeter to measure the EMF of the cell. The fact is because the cell has internal resistance that we cannot get rid of, except theoretically. Okay, so that is the equation that you can use to actually find out the voltage across the external resistance. So this voltage we call terminal voltage. Okay, terminal voltage. Alright, so this is the effect of internal resistance. Okay, and then the effect of internal resistance on the cell. So that's it for internal resistance. Alright.